So continuing my lectures on complex analysis, let us first start by trying to compute the value of this integral. So first we will write fz as equal to 1 by z to the power 4 plus 1, assuming and we will assume that this is being integrated over C1 plus CR, where C1 and CR are the following contours. This is your CR and this is your C1. Now we need to find out the residues. So first we need to find out the singular points. For that, let us again write the function fz as equal to 1 by z to the power 4 plus 1. So the singular points will be those points where z to the power 4 will be equal to minus 1. Now a complex variable can be also written as r d to the power I theta. So r to the power I theta t power 4 is equal to minus 1, assuming r is equal to 1. So it will be those places where that value of I theta t power 4 gives a value equal to minus 1. Now this is possible. I theta gets a value minus 1 when theta is pi, 3 pi, 5 pi and 7 pi, considering the 4 points. So since there is a theta here, so the singular points will be I pi by 4, I 3 pi by 4, I 5 pi by 4, and I 7 pi by 4, out of which only the first two are inside the contour. If you could see, this is where it is e to the power I pi by 4, and this is where e to the power I 3 pi by 4 can exist. So this is actually the value of theta. So now we need to compute the residues. So there are two singular points. One is to the power I pi by 4, and z2 stands for to the power I 3 pi by 4. So using now these are simple poles. So using the residue formula, the residue is limit for z1, limit z tends to z1, z minus z1 into fz, and so it is equal to again limit z minus z tends to z1, z minus z1, and fz is z to the power 4 plus 1. So here we will use L'Hospital's rule. So So we will just simply differentiate the numerator and denominator. So by doing that, what we obtain is limit z tends to z1 1 by 4 z cube, and if we put the values of z1, which is e to the power I pi by 4, if we put the values of z1 here and this one, then ultimately the value that comes here is e to the power minus I 3 by 4 by 4. And for the second case, second singular point, the residue for z2 is again limit z tends to z2 z minus z2 fz. The value comes out to be equal to e to the power minus pi by 4 by 4. So according to the residual theorem, the integral I is equal to the sum of 2 pi I into sum of the residues. So if we could expand it in terms of cos theta and sin theta, what ultimately we obtain is equal to 2 pi I minus 1 minus I by 4 root 2 plus 1 minus I by 4 root 2. So the ultimate value comes out as pi root 2 by 2. So the next thing that we will discuss is Taylor series. So for that, first we need to understand what is a geometric series is. A finite geometric series is a sum of the following quantities. Can be expressed as a 1 plus r plus r square plus till r to the power n. Plus r square plus till r to the power n. So it can be written as a plus ar plus ar square plus ar cube plus till a r to the power n. Or it can be written in summation form as summation j is equal to 0 to n a r to the power j, and again a j is equal to 0 to n r to the power j. Now this r is called the ratio of the geometric series. Now this geometric series is finite. Okay, now sorry, before that we need to understand that we need to find some that this sum of the terms where a is equal to a1 r plus r square till r to the power n, it can be expressed as equal to a 1 minus r to the power n plus 1 divided by 1 minus r. So how can we get it? We can see that if Sn is equal to a plus ar plus ar square plus ar cube till ar to the power n, then if we multiply Sn with r, then it will be ar plus ar square plus ar cube plus ar to the power n plus 1. And if we subtract these two series, that means if we say that Sn minus r Sn, then the only two terms will be present. One is the first term, this term, and this last term. So it will be a minus a up to the power n plus 1. So if we take Sn common here, so it becomes 1 minus r, and if we take a common here, so it becomes 1 minus r to the power n plus 1, and then Sn is simply equal to a 1 minus r to the power n plus 1 divided by 1 minus r. So this is the expression that we initially started with, and this is matching with this one. Now this is all about the geometric series which is finite. What about an infinite geometric series? The only difference between a finite and infinite geometric series is there is no last term involved in the infinite geometric series. That means to write S, we will not write any n here, so S is equal to simply a plus ar square and plus ar cube, and it keeps on going. There is no end to it. So we can write it as equal to a r to the power. So instead of writing here now j now is now from 0 to infinity instead of n as in the previous case. Now if the value of r is less than 1, then this series actually converges to, you can write a as equal to j is equal to 0 to infinity to the power j. This converges to a divided by 1 minus r. Now we will find the connection of this series to the Cauchy's integral formula. Now according to the Cauchy's integral formula, if z is analytic in a certain region, then we can express fz as equal to 1 by 2 pi I integration c f omega I omega minus z d omega. Z is equal to 1 by 2 pi I see omega d omega 2 omega minus z. Now this expression has this term omega minus z, so that is basically 1 by omega minus z, and this is equivalent to somehow like similar to a by 1 by r. The only thing is that we need to do some modifications, so we can either write omega minus z is equal to 1 by omega into 1 by z minus omega, and now this then becomes the ratio r equivalent to r, and we can expand it as in the case of infinite series. We can write it as 1 plus z by omega plus z by omega whole square and the ratio is here z by omega, and this is the condition where z modulus of z is less than the modulus of omega. Now if it is the opposite case, if the modulus of z is greater than the modulus of omega, then instead of writing as in the previous case, we can expand 1 by omega minus z as equal to minus 1 by z into 1 by omega minus z. So here the ratio is now omega minus z, so this gets expanded into minus 1 by z into 1 plus omega by z plus omega by z whole square, and the series continues. Okay. Now apart from that, there is something called a power series. So a power series is like this. You can expand fz. You can write fz as equal to n is equal to 0 to infinity an z minus z0 to the power n, and if we differentiate it, we have z. So if it becomes n to infinity n a to the power n z minus z0 to the power n minus 1, and if we differentiate it n times, then it simply becomes fnz is equal to n factorial an. So an is equal to simply fn z by n factorial. Now lastly, coming to the Taylor series. Taylor's theorem, I can call it. The function fz can be written as n is equal to 0 to infinity. So it is not minus infinity to plus infinity as in the case of Lorentz series. So and an z minus z0 to the power n, where an is equal to fn z0 divided by n factorial that we have previously found out. Now if we put the value of fn0 as in the derivative of if 0 in the derivative of 0, so it comes out to be 1 by 2 pi I integration c f z, sorry, divided by z minus z0 to the power n plus 1 dz. So this is the expression of the Taylor series.